Everyone, welcome back. So let's continue this series of problems on material science, focusing in on the mechanical properties of materials. And this time we're going to get some experience working with the actual graphs themselves and how we can use these graphs of the stress-strain behavior for different alloys to determine what's going to happen when we load them. So what we have a load of 85,000 newtons. It's applied to a cylindrical specimen of a steel alloy and has this behavior right here. And that steel alloy has a diameter of 15 millimeters. So the first question is, will the specimen experience elastic and or plastic deformation, and why? Well, if we're going to figure that out, we have to determine, did we leave this linear region? Okay, did we leave this linear region? If we did, we're most likely going to be a mixture of elastic and plastic. Because once we get past somewhere in here, it's going to have plastic deformation. So let's calculate it. First we calculate the stress and then go from there. So stress is equal to force over area. Area in this case is for a circle, and so it's pi d squared over 4. And when I plug that in my calculator, let me see what I get. I get an area of 176.625 millimeters squared. Perfect. Now, I'm leaving in millimeters because, millimeters squared, because 1 megapascal is equal to 1 newton per millimeter squared. I can't say it enough. This is a great conversion. Don't forget it. And so now I can just plug everything in. So I have 85,000 all over 176.625. So that stress comes out to be 481 megapascals. Now, if I'm looking at this chart right here, what you can see is 481 is way up here. It is off the scale on this first one. And so that is most definitely outside of that linear region. So that would mean for this part A that I have both elastic and plastic deformation. Some of it will be elastic. Up into that elastic point, all that's going to come back out. But everything beyond that point will be plastic. So just picking a random number here, let's say that everything right here, this is the elastic point, elastic limit, I should say. I could do it with a nice ruler. I forgot about this thing until recently. Okay, we'll just say that's my elastic limit here. So all of this strain will come back out when I release the loading. But everything beyond that, all the way up to here, all of this strain, let's just say that's 481, that will not come out. That is going to be stuck inside of my material. So it will be permanently longer. Okay, now we have to ask ourselves, well, for this loading, if it was originally 250 millimeters long, how much will it increase in length when this load is applied? Now, you might think, there's no way we can solve that. We actually can. It's not a horrible question. So how do we do that? We find 481 and we go across until I hit my curve. So I'm going to say 480 is right about there. Oh, maybe a little bit down. There. Okay. And now I'm going to go at a right angle from that point. And go down. Beautiful. And so, oh, that almost intersects perfectly. I'm going to pretend like it does intersect perfectly. And so I'm going to get a strain then of 0.02. So for B, my strain is equal to 0.02. I'm reading that just from the graph. I cannot use my Hooke's law at this point because that will not work. Let's see here. Yeah, looks good so far. So we want to figure out the change in length. So it was originally 250 millimeters long. And so remember that strain is equal to deformation over my original length. And this equation works no matter what. Like, it's not based on length. Just like the stress equation, stress equals force over area, that also works no matter what. So these two you can apply to anything. It's just a relationship between the two. If it's past that linear region, you have to use the graph. So going back to it, my deformation will be equal to the strain times my original length should be equal to 0.02 times 250, which is about 5 millimeters. There you go. So it went from being 250 millimeters long to 255 millimeters long when I loaded it. So there we go. Hopefully this gives you an idea of how you can use these stress strain diagrams to figure out the relationship when you go outside that linear region. And if you like the video, please consider becoming a member or a subscriber. Every new member helps me to continue making these videos and makes it more viable for the future. Have a good one. Bye-bye.